That's good.
All good. Alrighty. So, so my presentation today is just going to be a bit of an update on the progress that we've made in the beauty contest paper. So I just want to, just go through what we've been doing recently. So just for an overview, so I just want to go through quickly, recap what the project is about and just the basic ideas that we're trying to get across in our paper. So I'll do a brief introduction again, even though most of us probably already know what it is. So the idea is based around the Keynesian beauty contest, which is a beauty contest, consider a beauty contest of 100 contestants where two or more judges are looking to pick the 5 most popular contestants. So your most naive strategy in this game would be to pick the 5 best looking people who you believe. A better strategy would be to pick the contestants who you think other judges will pick. And an even better strategy would be to pick who you think the other judges will pick. And of course, you can take this level of iterative thinking or level of rationality up to infinity. And what you'll quickly realize is that your strategy is solely dependent on other people's perceptions and nothing about yourself or the intrinsic value of the contestants themselves. And this is where the link between the Keynesian beauty contest and the trading market comes in, where basically players in a trading or an economic sense aren't really worried too much about the value or the thing that they're trading themselves. They're more worried about people's perceptions of it, and that's really what dictates the value of the price. So the way we analyze this game quantitatively is by a game known as two-thirds guessing game. So in this game, everyone is trying to guess 2/3 of the average of all the other participants' input in this game. And we can represent an individual player's payoff with this function here, where you're taking the difference between an individual player's input and you're subtracting 2/3 of the mean. So how do we analyze this game? Or what does the analysis of this game actually end up showing us? So if this diagram here represents the level of rationality or the iterations of a player's thinking, a player who is level one rational, we'd say, their maximum bid price that they'd ever import would be 66.6 if the maximum value you can import is 100, because they're making the anticipation that everyone else is rational. So therefore, if everyone's guessing 2/3 of the mean, no one would go more than 2/3 of the maximum value. So that would stop it. That would cap their value at 66.6. And then if everyone else knows that, that would then bring your value down to 2/3 of 66.6, which would be 44.44. And you can take that to an infinite number of iterations, and eventually you reach all the way down to 0. This analysis here is the quantitative analysis of the previous slide, which shows that basically the dominant strategies which exist for players get smaller and smaller. The range of dominant strategy gets smaller and smaller all the way down to 0. And the way we do that is by taking some partial derivatives of the payoff functions and just setting that as our upper bound. I don't want to focus too much on this though, so I'm just going to go to the next slide. Okay, so initially, I don't think Kieran, you've presented your DV case to anyone here. So everyone's probably remembers the continuous variable implementation that we were looking to do initially. However, we've switched to a discrete variable case, which Kieran came up with. And the reason we've done that is because we want to implement this experimentally, and it is much easier to implement this type of game experimentally using discrete variables compared to continuous variables. So that's what we've been doing for the past few months. So how does our discrete variable game actually look? So the way the game plays is every player inputs their strategy or their bid, you might say, through the through this theta encoding. Now, players can play obviously between this 0 and this 1 state, and they have a range between 0 and pi for their theta angle here. And this is what the quantization circuit looks like. So every player starts off in a 0 state. they all become entangled using this J entanglement operator. Then every player implements their own individual strategy, which is their theta. And then this generates a wave function, which we can then take expectation values off for each individual player. And that expectation value will be their final bid in the quantum version of the game. So compared to our, so if I come back, yeah, so this was our classical payoff function here. And when we implement our quantization scheme, this is what our new quantum payoff function looks like here. So it's clearly a lot different, and it has some theta dependence, which is the player's input, and some gamma dependence, where gamma represents the level of entanglement. So in this discrete variable case, the level of entanglement that we can have is between 0 and maximum entanglement, which is pi on 2. So 0 entanglement should just give us the classical game. However, when we actually take gamma going to maximum entanglement, which is pi on 2, we see that the payoff function becomes completely independent of any input angle at all. And it's just dependent on alpha, where alpha represents, so in the 2/3 game, in the classical game, alpha is 2/3 exactly. So here it's just some arbitrary number, which I'll explain in a second. So obviously in this case, if every player has an identical payoff function, then there's no reason for players to play any type of strategy at all. It basically removes any equilibrium of the game, and therefore, as such, no player should tend towards either extrema. So no player should go race to the bottom or race to the top, which is what we were aiming for. Okay, so currently, after Kieran came up with his discrete variable quantization scheme, our next plan was to come up with some simulations and an experiment so that we can add some more meat to our paper. So we want to use these simulations as and this experiment as like a proof of concept for our work to show that it actually does work experimentally and theoretically. And the way we're going about doing this is using 3 different things. So we have 2 simulations and one human experiment. So they're all basically going to play very similarly to each other. So we want to start by playing the classical game in each case, and we want to verify the behavior that we expect. So we expect that every player should be racing to the bottom, for example, in the alpha equals 2/3 case. Then what we'll do is we'll make each one of them play the quantum version of the game, and hopefully what we expect to see is that we expect a few things. Either the players will take a longer time to reach the extrema, so it'll have like a delayed version of the classical game, or we expect there to be no equilibrium at all for the maximum entanglement case. So our first simulation that we ran is a deterministic simulation, which is just a basic computer algorithm. Our second simulation is a neural network simulation. So we have computers which are actually learning to play the games themselves. And then our final thing will be a human experiment where we have humans interacting with one another. So what does our deterministic simulation look like? So again, it's just going to be a basic computer algorithm which plays the game based on the classical and quantum utility functions. And what we're planning to do is have different players with different levels of rationality. And then what we can do is we can analyze the range of their playable values over multiple games or just one game. And then what we can do is we can plot that against, so we can plot their range of values versus their level of rationality. And what we hope to see is that as players become more rational, their range of values decreases all the way down to 0. So that's the classical case. And then in the quantum case, what we hope to see is either players will have scattered strategy ranges, so there's no equilibrium which tends to either extrema, or what we hope to have is just their entire range of values covers the entire range of all possible values, so no equilibrium at all. And that's what this would look like. So in this case, this is what we've actually Hugh's actually coded this here and generated this plot. And this is for the gamma equals 0 case. So this is just the classical game. And as you can see, as players become more rational, their range of strategies decreases towards the bottom, which is the exact thing that we'd hope to see. Now, for the quantum version, we're still working that out currently because we're getting some unexpected behavior, I think. And so for anything where gamma is greater than 0, so there is some form of entanglement, and we are playing a quantum version of the game, we'd hope to see something like this, where no matter how rational you are, your range of strategies still remains over majority of the game, over majority of all possible values, and there's no real distinct equilibrium. But we're still working that one out currently. So for the next simulation, which is the neural network one, Hugh did this code as well. It's basically employing an artificial neural network that has no prior knowledge of the game, and then just seeing how quickly these networks can actually learn to play the most optimal strategy. So for in the classical case, there would obviously be just the boom and bust, so you're going racing down to 0. And then for the quantum one, it could possibly be random. The next thing would then be to do developing plots similarly to what we just saw, but comparing their strategies over multiple game iterations. So what we'd expect to see is that over more and more game iterations, the machines should become smarter, and they should each learn more about the game, and they'll eventually tend towards the bottom. In the quantum version, what we expect to see is that it would probably take a lot longer to reach the classical outcome. And then for the maximally entangled case, we should see the AI learn absolutely nothing and just play anything pretty randomly. So Hugh's actually generated these plots here, and so far we think this works really well. So in this top left diagram here, we have gamma equaling 0. So this is just our purely classical game. And we have 9 different players playing the game. So as you can see here, players have a strategy to choose between 0 and 1, and they each start randomly depending on the seed that's chosen for the AI. And then after a certain number of iterations, they all quickly rush down to the bottom strategy to 0. Now, as we introduce some level of entanglement, it becomes slightly obvious that it takes a larger amount of iterations for the AI to reach the same strategy space as the classical version. And then you can see here as the entanglement gets even larger, like really, really close to its maximal value, it becomes extremely obvious that a larger number of iterations are definitely required for the players to reach the minimum value of strategy. And then at our maximum level of entanglement, so gamma equal to pi on 2, players will just stick to their initial strategy and they won't deviate from it because they can't maximize their payoff anyway. Because if we come all the way back here, they have no input basically on their payoff. It's just completely dependent on alpha, which is a preset value for all the players. So that's analyzing the neural network's strategy compared to the number of iterations that they play. Let's have a look at their payoffs compared to the number of iterations that they play. So for the classical case, all the players start at different varying payoffs, and then they quickly all obtain the same payoff because they all start playing the same strategy, which is just 0. So they all obtain a maximal payoff of 0. And then again, for a slightly larger entanglement, or for some entanglement, it takes some players slightly longer to reach the same payoff. So it's just like a delayed version of the classical game. And then over here, this one's pretty nice. This gamma equals to 0.45 pi, which is really close to maximal entanglement. Players seem to have differing payoffs for 10,000 iterations here. So it'd probably take them a lot longer to reach the maximal payoff of 0 here. And then for gamma equal to pi on 2, all players have the exact same payoff for no matter how many number of iterations here. So for the human experiment, currently we're still all just working out the details. Our goal is to perform our analysis for both the AI and the deterministic simulations, and then base our human experiment on what we learned from that. I don't think we've actually ironed out any details at all. The only thing that we do know is we're definitely going to have them play the classical game and then make them play the quantum game using some sort of qubit system. And I still think we haven't picked where we're going to be doing that as well. Our current suggestion is to play on IBM, I think. And yeah, that's about it. That's all I have.
Cool, thank you.
Thanks.
Yeah, I've got a couple of more comments. So I think, and this is for you as well as much as you, we haven't implemented single shot yet.
Yeah.
So if you go back to the neural network plots, so this will be based on the expectation value. I think that's why I think about this after our meeting. That's why it's not stochastic. So we definitely should do single shot. Single shot. This is an infinite shot. So we do single shot. That should be stochastic.
In terms of the single shot stuff, I played around with it in the deterministic, and I think it should be pretty similar to, like, in terms of behavior. It shouldn't deviate too much. I think it also in terms of stochastic, I don't know, the randomness and I guess over the iterations, if we separate the neural network from the game itself, so you have the agents in the environment, and then we implement something like a decaying explore rate, so allowing the neural network to explore a bit, then we would see the fluctuations as well, right?
And just to the first part, I think it will change quite a bit. So this is doing infinite shots, just because the expectation.
Yeah.
You do single shots, it's going to change quite a lot from this.
I guess when it goes to 10 shots, even let's say 10 shots, then it doesn't. Well, there is deviation. Yeah. Actually, yeah.
Yes, but like the big difference would be it won't be a continuous function as a number of iterations. It'll be stochastic. It'll be up and down, up and down.
Yeah. Okay.
Yeah.
And the other thing is, could you send this is outside work? This is for you. Could you send us, or either you send us the slides?
Yeah.
Well, I think maybe you send the slides. So I think we'll discussion about what you brought up today, tomorrow. And have some ideas. That's we need to. I mean, it's something. I mean, it won't be that difficult.
Yeah, for the deterministic case for this.
Yeah.
It kind of goes against all intuition.
I had a quick look at the so here's a result that the xi is just dependent upon the player's theta I, and he's right. So it works out that way, that the xi is like 1 minus cos gamma cos theta I for arbitrary gamma. So is this one. So
this one here.
In general, that maybe for this case it's true, but in general it won't be the case.
Yeah, definitely.
So you can understand that.
In terms of the mapping from theta to xj, it's an arbitrary choice. Right? We can make it's just that the mapping we've chosen in order to reproduce the classical game.
Yeah, so I noticed that, and I haven't been to the maths, but here I mean, that your p is explicitly for 0.
So gamma equals 0.
Yeah. So p of gamma, it would be a different function.
Yeah, it's that one. That one that writes the top left.
Yeah. Okay.
Yeah. So that's the quantum. I guess the quantity. They actually. Yeah, that's the actual terminology used, I think, from the papers, from the literature. They call that the quantity. The quantum quantity.
Any other questions, comments?
Yeah, I've got a question about the human experiment. Would it have to be like, first of all, what's the idea of what the humans will actually be doing? Do you have any idea of that at the moment? Like in both the classical and quantum?
Yeah, James, feel free to butt in here, but my interpretation is we'll tell them what the game kind of is, and then we get them to play the classical version of the game. So they're trying to select their own input bid, and then they'll put it in, and then they'll get a payoff back. And then based off the payoff that they get, they'll put in a new bid, and then they'll get another payoff back, and they'll see if it increases or decreases. And then what we expect to see is they'll slowly realize that their best strategy is to eventually go down as low as possible. Then in the quantum version,
So you're going to tell them you got to bid on this thing. It's worth something in between 0 and 100. And every time they bid, they get back some value, and then they go again and again and again.
I think so.
Is that the idea?
I think so. I think that's the idea. That's
the crux of it.
Yeah.
Mickey Kieran's has read up on the classical experiment. Are there any nuances?
It's basically that. Yeah. I mean, sometimes they don't even say like, here's an object to bid on it.
Yeah.
It's even more blatant than that.
Yeah.
Which is you need to try and guess 2/3 of the mean.
Yeah. Well,
Yeah.
I think
Just
the other thing that
you go.
The other thing I was going to say is, will you need to then do that 10,000 times, then bid 10,000 times to get these sorts of curves? Because I feel like that would be quite a long time for a human bidding 10,000 times.
Yeah, so that's the point of doing these simulations as well. So clearly, like, it's better with the deterministic one. You can probably play around with it a lot more, but hopefully you'll be able to get a plot where it's like, only after 10 iterations you can see the behavior that you expect, and then hopefully, you'd probably be able to reproduce that with the humans. Because obviously you're not going to play the game with them 10,000 times. And then the other issues with the quantum version, like James mentioned, like single shot versus, because if you wanted to determine an expectation value, it'd be really, really difficult. So that's another thing we have to consider as well.
Yeah, so we'll vary gamma with the entanglement and the number of shots to make sure that humans can produce some behavior which is not random in a reasonable amount of time.
Yeah. Okay. And the entanglement, what does that mean, like physically in the game? Like, do the
I think it would just be to do with the quantum setup. However you make the players play their game, the level of entanglement just represents the effect of each player's qubit on one another, like their correlation with one another, I guess. I'm not too sure about.
You can change in the quantum computing part of it.
Yeah, so the quantum computer will code it in.
Okay.
Yeah, hopefully it would just be like a universal gate kind of thing. Maybe you could, yeah. Oh, I have a question regarding the experiment literatures. So from what I've seen, it seems that the players will get a feedback of like the average value in order for them to adjust. Are there prior experiments where the players just given the payoff, the payoff? Kieran?
So I think trying to remember what exactly they were given. So I read this study about it was a Japanese group, I think. I'm pretty sure they just gave them the utility, so they just gave them the payoff. That was it.
Did they tell them what the game is?
That was the one where they just so blatantly said, there's going to be a bunch of people. They're going to guess the mean, so they're going to put in a bid, and you need to guess like less than whatever the average is.
Yeah, I reckon
we get the terminal.
We may want to get some input from psychologists who's done these things, but I I just not even I would want to do something like just tell the participants your goal is to maximize your utility, and that's it. And sit in front of the computer, they'll enter a value, and the computer will tell them what the utility is each time. And they'll then one step they go up, it just goes down. Then presumably the next step they'll go down, and if it goes up, then they'll just keep going down until thing. That's the most logical thing to do.
Yeah,
that's information I have.
It seems that that will require a lot more rounds. Right? It'll take more time for the experiment, for the people to learn, because it'll have less rational players in that sense.
Yeah, we'll play around. But if, for example, we have expectation value, then it will be quite obvious that things will go one direction if you keep decreasing, and they'll keep decreasing until thingo. But that's probably too simple. So then, but not everyone's rational. Some people will be superstitious and say, okay, maybe the third round will go up to increase. But then we'll complicate things with a finite number of shots. So if it's a single shot, then they go up and down, and they'll take longer to learn, definitely. But that's what these simulations are for. That's why the single shot will, 10,000 is way too much. Iterations. I'm sitting there playing a computer game. I probably don't want to do more than 20. I think.
This is dependent on the learning rate. It's arbitrary in terms of the iterations.
Of course.
But I suppose the question is, what's the learning rate of a human? So it's all well and good, like to put the learning rate to like 1 million or something and get this thing to converge in 2 iterations, but
yes, that's a good point. Yes.